Well, let's talk about how we can use vectors and inner products to represent functions and the role those might play in machine learning problems. So our goal is to introduce the notation that we use for vectors. We're going to review the idea of an inner product or a dot product between vectors. Then we're going to use these inner products to represent functions. Evaluate a geometric interpretation for both the vectors and the inner products between vectors. So in simple terms, a vector is a collection of values arranged in a row or a column format. If I have the vector w and it has elements 2, 3, and -1, we'll stack those vertically and in a column and call that a vector. Similarly, if I have a vector a who has elements a1, a2, a3, and a4, we arrange those vertically and call that the vector a. So we're going to denote vectors as lowercase letters with an underscore. And our convention is to assume that vectors are columns. So if I write W, I can assume that that is an arrangement of values in a column format. Now, sometimes we need to work with rows, and the way we'll denote that is to use the transpose operation. Now recall that when you take the transpose, you interchange the rows and the columns. And in the case of a vector, if I take the transpose of a column, that rewrites it as a row, as I've indicated here with W transpose and A transpose. Now it's just easier in terms of notation if one looks at a vector and you mentally think of that's always going to be a column. Now we can define the inner product, very important idea. The inner product between two vectors, here I've shown a vector A with n elements in it, A1 on up to AN, and then I've got another vector B with elements B1, B2, and so on up to B sub n. And we can define the inner product as the scalar C, which is the sum of the products of the individual elements of A and B. And it's very convenient to be able to write that as A transpose B. So this is the inner product or the dot product between A and B, and I can write that as the vector, the row vector A times the column vector B. Now it turns out it doesn't matter whether you write this as A transpose B or B transpose A. Basically, we can interchange the order of AI and BI because multiplication commutes with itself. One of the reasons inner products are so useful is that we can use them to represent many different types of functions. So let's take a machine learning problem where we have some data. What this is showing is someone's score as a function of the amount of time they took, say, on an exam. And what we'd like to do is predict the relationship between score and time. So we want to write the score S as a function of the time t. Well, let's try a couple different things, and we'll begin by defining a vector x with the score s in the first element and the value of the time t in the second element. And then I'll define another vector w that has two entries, w1 and w2. And I wonder, what does the inner product x transpose w equals 0 look like? Well, we can multiply x transpose times w, and that gives us s times w1 plus t times w2 equals 0. Now it's easy to rewrite that as a function of s. It's easy to rewrite this to express s as a function of t, in which case we obtain that s is equal to negative w2 over w1 times t. So this is the equation for a line with slope negative w2 divided by w1. And this particular line has y-intercept 0, so it's going through the origin. And I've sketched such a line in blue if we assume w2 to be equal to -5 and w1 to equal 6. This would be the line that we get. Now that isn't the greatest fit to this particular data set. We see that we're capturing the data up here at the large values of time, but not for small values of time. So perhaps we need to add a y-intercept and change the slope. So let's suppose we consider a second case where we define a vector x with first element s, second element t, and the third element, put the constant 1 in there. And then we'll define w to be w1, w2, w3, and we'll consider the inner product again being equal to 0. Well, now we have s times w1 plus t times w2 plus w3 equals 0. And you can rearrange this expression to write S is equal to negative W2 over W1 times T minus W3 over W1. So in this case, we have slope negative W2 over W1 and intercept negative W3 over W1. We have flexibility over both the slope and the intercept, and we obtain that by adding this constant down here and having a third variable. I've shown in green the case where W2 is minus 1, W1 is 2, W3 is minus 80. This particular line looks like it does a much better job of fitting the data than the one that we drew initially in blue. If you look at this data, you'd say, well, it's probably not really a line. It looks like it has some curvature to it. So maybe we should consider yet another case. Let's now define the vector x transpose. I'm out of room at the bottom here, so I'm writing this as a row vector. We'll define x transpose as s t raised to the third power, t raised to the second power, t, and then the constant 1. And similarly, we'll define w, and I'm using the transpose to indicate that I'm going to write this as a row. It's going to have w1, w2, w3, w4, w5. And if I consider, again, this inner product being set equal to 0, we see that with a little bit of algebra, we can rewrite S, and it becomes negative W2 divided by W1 times T cubed minus W3 divided by W1 times T squared minus W4 divided by W1 times T minus W5 divided by W1. So in this case, we have S is a cubic polynomial or a cubic function of the time variable T. I didn't specify values here, but as we allow S to be polynomial functions of T, we're going to be able to capture some curvature with our approximation. Now, this is a very important concept that applies to pairs of vectors. We say that a vector x and a vector w are orthogonal if and only if their inner product is 0. Now, you may recall from the dot product or the inner product definition, having seen this before, that the inner product of x transpose times w is equal to the magnitude of x times the magnitude of w times the cosine of the angle between the two vectors. Inner product gives us the projection of w along the direction of x. Here, what I've written in parentheses is x divided by the length of x, so that's a unit vector pointing in the x direction, and we're going to scale that unit vector by the inner product x transpose w, and that gives us this value here. And you can go through the trigonometry that corresponds to this to see that this all works out. This angle theta tells us the relationship, the angular relationship between w and x, and it's sort of independent of the length. Okay, I can make w shorter or longer, and as long as it points only in the same direction relative to x, the angle isn't going to change. So if the two vectors are orthogonal, in other words, x transpose w is equal to 0, then this angle is 90 degrees, or pi over 2 radians, because cosine of pi over 2 radians is exactly 0. And the vectors still have non-zero length, but since the inner product is 0, that means the angle has to be 0. Now, if I consider the set of all values of x for which x transpose w equals 0, where I have axes x1 and x2, I have some vector w, and I want to know what is the set of all x that are orthogonal to w. Well, it turns out that that's a set of x that lie along this line. And if you do the inner product, you find that for the inner product to be 0, we have to have x2 equal to negative w1 over w2 times x1, and that's just the equation of a line through the origin with slope negative w1 over w2. Geometrically, that this looks about right. If I have a line that's perpendicular to w, then the inner product is always going to be 0 because the projection of w onto any vector that lies along this line is going to be exactly 0. Okay, so this gives us a line, which is something we used in the example a moment ago when we were looking at fitting that data. Now, these same geometric concepts of orthogonality and angles between vectors and so on, they apply in higher dimensions than 2. It just becomes more difficult to visualize and to draw. So I'm going to try to do 3 dimensions here. And if you have a vector x that's somewhat pointing out of this plane of these two coordinates, and a vector w that's kind of pointing back, then I can define the angle between those vectors, and that's going to be based on the inner product, the magnitude of x times the magnitude of w times the cosine of theta. And so this angle is in the plane that is defined by these two vectors. Consider the case where we have orthogonality. If I have 3 dimensions and I have x1, x2, and x3, and I want to ask what is the set of all values of x1, x2, and x3 for which x transpose w equals 0. So w is some fixed vector. We did this in 2 dimensions, and we saw the answer was that it was a line which was perpendicular to the vector w. Well, in 3 dimensions, you can see here I've sketched the w somewhat coming out of the frame of the video. I've sketched one particular vector x that is orthogonal to that w, forms a 90-degree angle with respect to w, and clearly I can rotate this vector x around that axis formed by w, and I'll always stay orthogonal. Okay, so what this means is that the set of x for which x transpose w equals 0 ends up being a plane that's orthogonal to w. And that plane goes through the origin. So x equals 0 is included in the plane. The same concepts apply in arbitrary dimension space. It just becomes more and more difficult to draw and to visualize. The inner product, x transpose w, if x has 10 elements and w has 10 elements, then x transpose w is equal to the length of x times the length of w times the cosine of the angle between x and w. Of course, the length can be written as the square root of the sum of the squares of the elements, which is just x transpose x square root, and w is w transpose w square root. We saw in 2 dimensions that this condition x transpose w, the set of all x, formed a line perpendicular to w. In 3 dimensions, we had the set of x such that x transpose w is equal to 0. That formed a plane which was perpendicular to w. And it turns out that in n-dimensional space, this condition gives us an n-1 dimensional space that's perpendicular to w. Here we had a 3-dimensional space, and our set of x was a 2-dimensional space perpendicular to w. And when we were in 2 dimensions, we had a 1-dimensional space. So this orthogonality, the set of all values that are orthogonal to w, forms an n-1 dimensional space. That is a difficult notion to visualize. So let's visit another application of some of these inner product ideas. And let's suppose we want to classify someone with respect to their likelihood of having heart disease. We're going to let x1 be the feature systolic blood pressure. We'll let x2 be the total cholesterol feature. We've collected data for people that have heart disease and don't have heart disease, and I've plotted it here. Pluses representing heart disease, the circles representing people without heart disease. And as you might guess, that if your blood pressure is lower and your cholesterol is lower, you have a tendency to be less likely to have heart disease. So that represents this group down here. This is data where we know the answer, we know the correct answer, we know who has heart disease, we know who doesn't. What we'd like to do is collect some new data point where we didn't know the correct answer and predict whether that person with that measurement has heart disease or is not likely to have heart disease. So we need to decide, if we collect some measurement, which group does it fall into. And in order to do that, we need a decision boundary where we're going to decide that if it's up or right of that boundary, then the person probably has heart disease. If it's to the lower left, they probably don't have heart disease. We can describe such a decision boundary is using inner products. Let's suppose we think that a line does a pretty good job. So our line, then, the form of a line, we can write the x2 as some slope times x1 plus a y-intercept b. And this can be expressed in the form of an inner product, x transpose w equals 0, if I define x as my total cholesterol, x2, my systolic blood pressure, x1, and then I throw in this constant, which I need to get the y-intercept, and then we'll let w be equal to 1 minus m and minus b. This inner product then gives us this exact equation. So if we take a sample measurement from somebody we don't know the truth about, we've figured out what w is from this data, then all we have to do is do the inner product of x transpose w. If x transpose w is greater than 0, that means they're above the boundary, or likely in the heart disease category. If the inner product x transpose w is less than 0, then we would classify them as not having heart disease. Problem of how we find a good w from this training data is something that we'll look in depth at later. Now maybe you look at this and you say, well, I don't think that a line is maybe the best boundary here. It looks like there's some kind of curvature here that even if you have low blood pressure but your cholesterol is really high, you might have heart disease. Or if your cholesterol could be low but you still have really high blood pressure, you're likely to have heart disease as well. And let's suppose we decide to use a third order polynomial. I might express a third order polynomial as x2 is c1 times x1 cubed plus c2 x2 squared plus c3 x1 plus c4. That's an arbitrary third order polynomial where x2 is a cubic function of x1. Well, again, I can write this, as we saw earlier, I can write polynomials using the inner product formulation. If I define x, so that I'll put x2 in the first position, I'll put x1 cubed, x1 squared, x1, and then 1. In w, I'll put 1 minus c1 minus c2 minus c3 minus c4. And then this inner product, x transpose w equals 0, will give me exactly this equation. And for some choice of C1, C2, C3, and C4, I should be able to get a boundary that may do a better job. The boundary is defined by x transpose W equals 0. So if I obtain a set of blood pressure and cholesterol values, I'm going to plug those into this vector x, and then I'm going to use the W that I found to separate these two regions, compute x transpose W. If it's greater than 0, that means the measurement lies above and to the right of the orange dashed line, so I'm going to likely to classify that person as having heart disease. If it lies below that, in other words, x transpose W is less than 0, then I would classify that person as not being likely to have heart disease. So inner products provide a super useful tool for us to systematically describe a lot of functions, particularly the kinds of things that come up in machine learning. And because inner products are fundamentally associated with matrices or matrix algebra, it allows us to use the very powerful tools of linear algebra to solve many of these problems.